My students, welcome. Today we are discussing about Otto cycle and its derivative expression for and standard efficiency. First, the history of Otto cycle. The first person to build a working of four-stroke engine, a stationary engine by using coal gas and air mixture for fuel, was German engineer by Nicholas Otto in 1861. So, Otto cycle, it is one of the idealized thermodynamic cycle, and it's applicable in all the automobiles, especially in SI engine. So already we have discussed about SI. What is meant by SI? So it is the spark ignition engines. So it's nothing but it's a petrol engine, or otherwise it's a gas engine or gasoline engine, like that. So first one. So in Otto cycle, it consists of the four important processes are there, but already the engine process we know that the suction, compression, power and exhaust. But each and every process, during that every process, what are the thermodynamic processes happens? Okay. So we know that already we are discussing about the thermodynamic process also. So what are the constant volume process, constant pressure process, isentropic process, polytropic process, etc. Out of that, in that thermodynamic cycle, what are the processes, especially in Otto cycles? So it consists of four processes. So in that four, the two isentropic process and two constant volume process. Isentropic process, already you know that, okay, it is nothing but it is a adiabatic, but it's reversible adiabatic. And last class we are discussing about what is the basic difference between adiabatic and isentropic. Adiabatic is nothing but no loss of heat or no gain of heat. That's one. Maybe it is a reversible or irreversible. But in isentropic process, there is no transfer of heat. It is adiabatic only. But there is no transfer of heat. It is only reversible. So it is the reversible adiabatic process is nothing but isentropic process. So nothing to worry. So in Otto cycle, it consists of four. Already we have discussed the four important processes. So two isentropic process, two constant volume process. The constant volume process is nothing but isochoric process of. That's one. So what are that? So here we are discussing about here. Okay, they mention in PV and TS diagram also. So here that the y coordinate is considered as a pressure and x coordinate is considered as a volume. So pressure, volume. Okay, similar case. Okay, here another one in TS diagram. Okay, so the y coordinate is considered as a temperature T and x coordinate is considered as entropy S. Okay, so now, so in that one, so in that PV diagram, so what are the curves is represent the process, it indicates in the curves it represents. Okay, first one, the 0 to 1, it is a suction. 1 to 2, it is compression, especially here the compression based on that isentropically. So therefore it is called 1 to 2, it is isentropic compression. Next 2 to 3, okay, it is the line is vertical. Okay, vertical line, that is constant volume process. So therefore 2 to 3 is a constant volume process. Next 3 to 4, again the curve, it is isentropic expansion, and 4 to 1, it is a vertical line, it is constant volume process also. So now it is based on that 0 to 1, 1 to 2, 2 to 3, 3 to 4, 4 to 1 and 1 to 0 again. So here the 0 to 1, it indicates suction. Okay, so the suction is constant pressure only. So already we are discussing about the four processes in Otto cycle. So two isentropic and two constant volume process. But technically the additional two process also is there. The two process is constant pressure only. Okay, where the two process, especially the constant pressure process, means one is 0 to 1, it is suction. So in SI engine, air fuel mixtures, okay, to suck. Okay, through carburetor, already we are discussing about in SI engine in last class. Okay, through carburetor. So the air fuel mixture is entering 0 to 1. okay, suction. So at constant pressure. So default they consider as a atmospheric pressure P1. So constant pressure, the suction, okay. Similar case, the finally, that is 0 to 1, it is a constant pressure during suction. Similar case in final, after completion of that end of the cycle, 1 to 0, it is exhaust. So therefore, the technically the two constant pressure process also is there. Okay, 0 to 1 and 1 to 0. That is 0 to 1, it is a suction of mixture. Similarly, finally, 1 to 0, it is a exhaust from the engine. Now, so the works takes place between that 1, 2, 3, 4, 1. So here the 1 where it indicates. So now, so before we are discussing about basics of engine. So the engine, it is a piston cylinder arrangement. Okay, when the piston is top dead center. Okay. So with already the clearance volume is there. Okay. So now the piston is at top dead center position. So during that suction, the piston moves downwards, that is TDC to BDC. Okay. So the stroke length L between the distance TDC to BDC. So consider that volume, that is called stroke volume. So it is also written, it is called as a swept volume. It denoted by a letter V suffix S. But already initially the clearance volume is there, that is VC, clearance volume. So when the piston moves from top dead center to bottom dead center, the volume is increasing from VC, that is nothing but clearance volume, to V1, stroke volume. So therefore the sum of clearance volume plus stroke volume, it is nothing but total volume. Now the piston, okay, so in PV diagram it indicates from 0 to 1. Okay, it is total volume is total volume, that is nothing but total volume VC plus VS. Okay. During that compression 1 to 2, it is a compression. The compression takes place isentropically. So during that initial isentropic starting point to 1, okay, up to the state 2. So at 1 V1, that is volume V1, at a corresponding points or state the pressure P1 and corresponding points the temperature T1. So therefore the V1, P1, T1 points. So during the compression, isentropic compression, already we are discussing, we know that isentropic, it is PV power gamma equal to constant isentropic process. So during isentropic process, the curve 1 to 2, it indicates isentropic process. Okay. So what happens in isentropic process? It is a compression. So the piston moves from bottom dead center into top dead center. Therefore the volume is reducing. So if the volume is reduced, that is due to that the reduction of volume, the pressure automatically is increasing. We know that the pressure is increasing means it default the temperature also is increased, because we know that the pressure is inversely proportional to volume. The pressure is directly proportional to temperature also. So therefore the volume V1 to V2, due to the reduction of volume, the pressure is increased from P1 to P2 during compression. At the end of compression, the heat will be supplied. So it's nothing but the spark will be ignited. Already the compressed air fuel mixture is ready to fire. At that time the spark will be ignited, because it is thermodynamic cycle is applicable in SI engines. So therefore from spark plug, the spark will be ignited. Like it's nothing but heat supplied. Okay, when it takes place during constant volume 2 to 3, it's represented in that PV diagram. So during 2 to 3 at constant volume, the heat is supplied. That is nothing but the air fuel mixtures are going to fire. It is the combustion takes place. At the end of compression, the spark will be ignited, the compression takes place. So therefore the pressure is increased at constant volume. V2 is equal to V3 during that. So after combustion, okay, the power will be starts. It's nothing but expansion. It is also called as working. So during that working, okay, the curve is represents 3 to 4. It indicates isentropic expansion. Then, so the works takes place at the from point 4 to 1. It is heat rejected. So it is denoted by a letter QR. The heat supplied 2 to 3 is QS and heat rejected 4 to 1. it's QR. So during that 1 to 2, during isentropic compression, the work takes place, that will work input. Similarly, 3 to 4 expansion, the power output. So that is nothing but work output. So 1 to 2 it is a work in, 3 to 4 is work output. Similarly, 2 to 3 is the heat supplied, QS, and 4 to 1 heat rejected, QR. So finally it's represent the total PV diagram, 0 to 1 suction, 1 to 2 compression. At the end of compression, that heat will be supplied. Now the combustion takes place, the power starts. 3 to 4 is expansion, is nothing but power, and 4 to 1 at the end of power strokes, the exhaust gases is ready to leave to the atmosphere, okay, up to the pressure P1, okay, then P1 to, that is point state 1 to 0, it is exhaust at constant pressure finally. So already we are discussing about, okay, so the 4 important process. Additionally, technically another 2 process also is there, that is suction and exhaust by constant pressure only. So during that 1 to 2 isentropic compression, already we know that isentropic is nothing but entropy constant. Entropy constant, already we have discussed. What is the difference between adiabatic and isentropic? Isentropic, there is no transfer of heat, therefore Q value it is 0, therefore Q 1 to 2 is 0 because there is no transfer of heat. So already initially we have discussed about it is idealized thermodynamic cycle. So let us consider it is ideal. So it is therefore there is no transfer of heat. So therefore Q1 to 2 is equal to 0. Next 2 to 3, it is a constant volume process. During that the heat will be added. So therefore the 2 to 3 stands heat supplied at constant volume. So already we discussed about the basics of thermodynamics. Okay, during that constant volume, the Q is equal to mCv delta T. So where M equal to mass of the gas is nothing but air fume mixture, Cv specific heat at constant volume, and delta T change in temperature. So the process between 2 to 3, therefore the temperature T2 and T3. So it also the represents in TS diagram. So 1 to 2 work input, vertical line, because it is isentropic, therefore entropy is constant, S1 is equal to S2. Next 2 to 3 heat supplied to the system, heat supplied, so 2 to 3. Next the 3 is the maximum temperature. Okay, after at the end of the combustion, okay, the temperature is the maximum during the firing of air fume mixtures. So it is a T3 is nothing but T max. Next 3 to 4, it is the work output, that also it is isentropic expansion, therefore S3 is equal to S4. And finally 4 to 1, it is heat rejected, correct, that's what. So here the PV diagram it represents, and there in TS diagram also it's mentioned, okay, so that's what. So here the 1 to 2 is a constant, 1 to 2 is a isentropic compression, there is no transfer of heat, and 2 to 3 it is a heat supplied, that is mCv delta T is nothing but the 2 to 3, therefore it is mCv T3 minus T2. So between the 2 to 3 the maximum temperature is 3 and minimum temperature is 2, therefore the difference between T3 and T2, therefore Q 2 to 3 is nothing but heat supplied, QS is equal to mCv T3 minus T2. Next 3 to 4, it is isentropic expansion.